Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to talk about the control problem for manipulators. So this is how the today's presentation has been organized. So initially I'll be talking about the control problem for manipulator, followed by what practical considerations we should have in mind, such as feed-forward nonlinear control, dual rate computed torque implementation, and lack of knowledge of the manipulator parameters. Then we'll look at the current industrial robot control systems and followed by Lyapunov stability analysis. So, the control problem for manipulator, you see, as we have seen, the manipulator dynamics contains these terms. Basically you have the inertia coupling, you have Coriolis effect as well as the centrifugal effects terms, then gravity loading is there and the friction is there. Okay. So all these terms contribute to the manipulator dynamic equation or the manipulator torque requirement, and this equation becomes complicated for the multi-joint robot. So if a robot has got many degrees of freedom, then this becomes further complicated, right? So this is what we have seen, or this is the equation which I have been talking about, and this figure is about, say, a two-arm manipulator with you can see here these tau 1 and tau 2 are the joint torque, and you have the inertia coupling being indicated here, Coriolis and centrifugal coupling, as well as the gravity loading has been indicated in this figure. Okay. So here we know that this is the mass matrix term, this is your Coriolis plus centrifugal term, and this is the gravity vector, and we have the joint torque vector. Okay. So if we want our torque requirement more realistic, we need to consider the friction terms as well, and we have seen that the friction can be very nicely modeled if it is modeled as function of theta and theta dot. Okay. So F theta theta dot is friction non-rigid body effects. So the problem of controlling such a complicated system can be handled by the partition controller, which we have already seen earlier, okay, during the linear control and the non-linear control lectures. So I can write the partition control law here as alpha tau dash plus beta as the tau. Here this alpha is same as this m theta, right, and rest of the part constitute as the beta. Okay. Alright, then I can write the servo law portion as this one, where is the error, basically error vector, E derivative is the error derivative vector, and theta d double dot is the joint acceleration vector. So this is how things could be represented in the through the block diagram. So you have the arm, you get theta, theta dot values from here. You have the desired value of theta here and desired value of theta d dot. You take the difference over here, okay, of theta and theta d, similarly theta dot and theta d dot. So you get the error and error derivative here, multiply with the gain kp and multiply with the gain kv here, okay, and then sum up both of these with the theta d double dot. Okay. So this is what you get, the tau dot. Okay. And the previous portion which I have shown over here, okay, so that comes from this part. Okay. So I can evaluate these values for the different values of theta and theta dot and enter it here, and this tau dot being multiplied by m theta, okay. So and when added over here, that gives me the tau. Okay. So these terms I have already explained. This Kp and Kv, these are going to be the gain matrices in this case. Okay. So the final closed loop error equation will looks like this one here. So you have the double derivative of the error, you have the derivative of the error, and you have the error vector here. Okay. So this is for the multiple number of joints, and if I am talking about a single joint, then I can write these values for the say ith joint, the expression will be this one. Okay. When we are going for the practical implementation, there are so many things which need to be considered. Okay. So, you see, the ideal nonlinear control law assumes that we are having the continuous time computations are there. We know everything about the model. Means what? I know the mass matrix very precisely, I know the friction very precisely, okay, and there is no delay in sensing or actuation, okay. So, this is what we are assuming, alright. But in practice, you see, these assumptions are not true, as all of us know. There are two major problems. One is computation time, okay. You see, the model based control needs many calculations, alright, that we have already seen, okay. And the model inaccuracies because are going to be there, because the real robot never matches the model perfectly. There are parameter change with load, okay, wear, friction, there is uncertainty. So many things are going to be there. So, it is difficult to precisely know the model, okay. And moreover, when we are going for sampling and digital implementation, okay, you see, the real manipulators are going to be controlled by digital computers, okay. And so naturally, these are digital devices, so control cannot be the continuous one, truly continuous one, okay. So, what? The control is performed at a definite sampling rate, alright. So, sensors are read at discrete instant, okay, and commands are updated at discrete instant. Then sampling introduces, we are sampling a signal, okay. Then there are many other things which come along with that. What are those? You have the delays, right? We have the approximation, because continuous signal we are doing representing in a discrete way, okay. So, or vice versa. So, you have the approximation, and so there is a performance degradation, okay. You see, if your sampling is at the slow rate, then naturally your control quality drops, okay. Tracking becomes poor, it is quite obvious, and stability could be affected. And if your sampling is fast, then naturally we are going to be more close to the continuous time assumptions which we usually follow, okay. So, this is what the model based manipulator control system which we have seen. Now, let us see how can we do the feed forward nonlinear control for this one, okay. So, in this figure you see that this is the model based portion, alright, and this one is your servo portion, okay. So, in feed forward control, what we can do is that we can take this servo portion inside, okay. In the model based portion, you see the servo portion is outside. So, we can take this servo portion inside and take the model outside, okay. So, one way to improve practical implementation is to place the dynamic model outside of the servo loop, as I just told here, okay. And in this one we can give from the trajectory generator the trajectories for position, velocity and acceleration over here. And so, the dynamic model gives you the torque basically, alright, and this torque is then added up with this servo loop torque, and then that command is supplied to your arm, okay. So, the model produces the feed forward torque basically, okay, and the servo loop adds corrections using the error feedback from here, whatever is coming. So, this error feedback is incorporated into the servo loop, okay. So, basically this torque is actually the model based torque which I am getting from here, and this torque value which I am getting from my servo loop, that is from this portion, okay. So, from the feed forward scheme, the closed loop error equation turns out to be of this form, okay. If you do some algebraic manipulation, you will see that this closed loop error equations turns out to be of this form. Now, here by doing this, what we have achieved, okay, what we have achieved, we could get the fast servo loop, then the model computations can be done separately, as we have taken that to the outer side, okay, and the model based torque can even be pre-computed offline. Offline we can have the pre-computation, okay, and then those values could be added up with the servo loop, okay. And of course this is very much useful when the trajectory is known in advance. So there are some important observation, and that observation with this equation is that this is not completely decoupled equation. Alright. So here this m inverse theta, this one term you see makes the pole depend on the configuration. Okay. So the effective dynamics change as the arm moves basically. Okay. Next, let us see the dual rate computed torque implementation. So here the main idea is that the model based control computations are expensive. Okay. So computing full manipulator dynamics at every servo cycle may be difficult, right. So can we think of something like this, that we run the model computation at say slower rate, okay, which is nonlinear dynamic model computation, and this could be a background process which is done in the background, and the servo portion we run the servo feedback loop at a faster rate, and the error correction is done by the servo feedback loop. And the dynamic model is expressed in the configuration space form. We have seen configuration space form means your all the model parameters represented as function of thetas. Alright. So you have m theta here, you have b theta, c theta, g theta, like that. This is what is called as the configuration space form. Alright. So this portion can be computed by the background process. Okay. So what are the effect of external disturbances? Alright. As I have been telling that many a times we lack the knowledge of parameters, alright, and in that lacking the external disturbances also could be there. What could be these external disturbances? These could be the variation of the payload, okay, some external forces coming, say your robot tip hitting some unknown object or obstacles, okay. There could be the change in friction, friction changes, vibration could be there, or my model has got some unmodeled dynamics. That could also be the possibility. Alright. So, how could I take care of these? So, let me summarize that I have the disturbance torque which I give as tau d, okay, and say this is the disturbance torque vector. So, in this model this is how I introduce that disturbance, okay, alright. So, I introduce that disturbance, and with the aim that it takes care of the lack of my knowledge about the parameters, okay. Then the error dynamic equation looks like this, where this tau d is what is coming from here, the disturbance, okay, and these disturbances directly excite your tracking error. So, in case of steady state condition, what happens is basically your this term becomes equal to 0. So, your E is Kp, I can take right hand side. So, that will be Kp inverse, m inverse and tau d, okay. Yeah, here because m theta is not diagonal, here the disturbance at one joint affect the other joint, okay. So, that is the challenge which is going to be, okay. Other lack of knowledge parameters, the model uncertainties, and here as I said we may not be able to know the perfect knowledge of the model, okay. And what do you mean by perfect knowledge of the model? Perfect knowledge of the model means that whatever is the actual one, okay, I know the same, alright. Whatever is the actual centrifugal and Coriolis terms, I know the same. Whatever is the gravity, that is gravity is also same, as well as I am fully aware about the friction modeling, okay. So, these are say the our model which I am assuming, and these are the perfect model, okay, which it should be. So, actual manipulator dynamic equation, this equation we are already aware of, right, and so the controller uses the approximate model, okay, because for the controller the parameter value should be known by me, right, okay. So, what I know as this is m cap theta for the alpha, and these are for the beta, right. So if I put these values and get the closed loop equation, this is what it turns out to be. Okay, so this is what it turns out to be. So these terms are coming because of my lack of knowledge about the parameters. Okay, so what happens because of this, the perfect decoupling will not be achieved. So next let us see the current industrial robot control system. So here is the one industrial robot, say Scorbot, which is available in our lab. Okay, so in practice many industrial robots do not use the full nonlinear model. Okay, why? Because model computation is expensive. Okay, and parameter knowledge is incomplete. Simpler control laws are often good enough. Okay, most industrial robot use simple robust control architecture. Okay, and no full decoupling is done. Okay, joint is often treated almost independently, and controller gains are chosen to give acceptable performance over the workspace around. Okay, so here the individual joint PID control, if you look for, okay, so in this one we can have the alpha value as I and beta value as 0. So the servo control law becomes this one. Okay, we have seen this form already. This the integration of the error term, this one I am adding over here, where this is Ki is the integral gain basically. So this becomes the servo law. Okay, and yeah, so here often theta d double dot is 0, as this is not available, so often we do that assumption. Okay, and this is how the current industrial robot are controlled. So you have the joint, you get the theta and theta dot value from here through sensor encoder. Okay, we have the desired value theta d. So here you get actual value of that. Here you calculate the error, right? So multiply that error with a gain. So you have the KPET, here KV and the derivative of the error, right? And here Ki and integral of the error. So all these are summed up, and so you get the joint torque over here. So this is how it is implemented in industrial robot. Here you see KV, KP, Ki are diagonal gain matrices. No model based compensation is used here. Okay, each joint is controlled as a separate system, and this is essential a PID type joint controller. Okay, so if we look for the performance of simple joint control, so because say there is no decoupling here, as I said, okay, one joint motion is going to affect the other joint, and the rejection of the disturbances is not perfect. Okay, so and fixed gain cannot give ideal critical damping for every robot posture. Okay, so hence we go for the average gain values. And if you want to have the compensation for the gravity as well, then in this control law I can add this gravity term also. Okay, and you see gravity creates steady state error, and if I add this one, it improves the holding accuracy, and this is how a common industrial improvement over PID is carried out. Next, let us see the stability. Okay, so a system is considered to be stable, okay, if over a period of time error is not accumulating, right? So in the Lyapunov stability analysis, the main idea is that we need a method that can prove stability without solving the differential equation. See, the general way is that you have a system differential equation, right? You solve that equation and see whether with time the errors are increasing, okay, or decreasing. If with time the error is increasing, then naturally your system is going to be unstable, right? But the beautiful thing with the Lyapunov stability criteria is that you need not solve the differential equation, okay. So without solving the differential equation, one should be able to tell whether your system is going to be stable or not, all right. So this method uses an energy like function, okay. So if a positive function keeps decreasing, along the system trajectories, the system is stable. Okay. So, something to note that stability is not the same as the performance, alright. A system may be stable, but still responds slowly or poorly, okay. And the Lyapunov analysis tells us whether the system will settle, not how fast in every detail, okay. So, to give the example for this one, okay, we can take the simple spring mass system which we have been considering throughout, like this one, okay. So, K is the spring stiffness, B is the friction over here, okay, and say M is the mass, and say this is my x direction, okay. So, the system equation for this is going to be this one, we have already seen. So, for this system the total energy is going to be the kinetic energy of the mass here, which is half mx dot square, and the potential energy of the spring, which is half kx square, okay. And you see, so here if I take the derivative of this total energy, what I get here is mx dot x double dot plus kx x dot. And now substitute the system equation, say mx double dot as from this one, we get this term. If we substitute, this means that your v dot, this mx double dot I want to substitute, okay. So, this will be x dot minus bx dot minus kx, okay, plus kx x dot actually. So, this is minus b x dot square minus kx x dot plus kx x dot. So, these two terms get cancelled. So, this is what I get v dot as minus bx dot square, and you see b is the damping. So, if your b is going to be greater than 0, your v dot is going to be less than 0, okay. So, your rate of change of energy is going to be negative basically, okay. That is, the energy keeps decreasing, and so if the energy keeps decreasing, naturally your system is eventually will be coming to rest, okay. So, from here you see, to find the rest position, these two terms will be 0 at the steady state, your kx is going to be 0, okay, or your x is going to be 0, okay. So, the previous analysis is a very simple example of a more general technique, what we call as the Lyapunov stability analysis, Lyapunov second or direct method, okay. So, you see, for the general nonlinear system given by this one x dot as fx, say x is the state vector and fx may be the nonlinear term, okay. The Lyapunov function must satisfy this condition, right, that it is continuous and has continuous first partial derivative, and this value is greater than 0 for all value of x except for v at 0 is equal to 0, and along trajectories this value is less than 0, okay. So, if this is less than 0, then definitely you have the asymptotic stability, okay. So, here you see Vx acts like a stored energy, and if it always decreases, the state cannot grow without bound, okay. And so, the state is pulled towards equilibrium. So, this is the basic idea of the Lyapunov stability analysis, okay. Let us take an example, okay. So, consider a nonlinear spring damper system with the system equation as this one, okay. And here say this is the nonlinear damping and this is the nonlinear spring force, okay. And the damping and spring force satisfy this condition, that is they are greater than 0, this one for x dot not equal to 0 and this one for x dot not equal to 0, okay. So, we can construct a Lyapunov function something like this, okay, half x dot square plus integral of say k lambda d lambda, and so we can differentiate the Lyapunov function, okay. So, this is the Lyapunov function which we have assumed. If we differentiate with time, this is what I am going to get, right. And here I can write, take this x dot common. So, this is what is left inside, and for the system which we have assumed over here, Okay, this is my system equation. Okay, so if I rearrange the terms, this is what I get, that is x dot double dot plus kx is going to be minus bx dot, and if I substitute this over here, so this is what I am going to get. Okay, so since x dot b is greater than 0, your v dot is going to be less than 0. Okay, so this again the same thing, that is energy never increases and your system is stable. Here are some of the observations. So if your this v dot is 0, then your x dot is 0. Okay, but it doesn't mean your x is also going to be 0. Okay, so we must check whether trajectories can get stuck away from the equilibrium condition. For all trajectories, that is for x dot equal to 0, if you take this equation, okay, for which x dot 0 is the only solution. Okay, that means that system is rest when you have all these terms being equal to 0. So to summarize, in this lecture we studied the control problem for manipulator and the nonlinear rigid body dynamics of the robotic arm. We explored important practical consideration, studied the current industrial robot control systems, introduced Lyapunov stability analysis and applied Lyapunov analysis to linear and nonlinear systems. Okay, so for further reading, you can refer to J.J. Craig, Introduction to Robotics, Mechanics and Control. With this, I would like to close for today. Thank you. See you in the next lecture.